They have no carbs. Yes, they are.
Algorithms are
Hello. Too close.
Okay.
Comprehensive. Jeez.
You find out it's comprehensive, so go look at all this stuff that we saw at the beginning, right? But do.
nice try, Lena.
But I'm not gonna go over it today. But and I have some sections for you to look to focus more deeply in. For the other stuff, I'm assuming that you have been reading the book, and so just reading should be enough. You don't have to memorize it, right? Just have a clue. But on those, you need to study. If you haven't been reading the book, then you're in for a fun week over Thanksgiving.
I distinctly remember you saying we didn't need to read the book on the first day of class. So.
Oh, yeah. It's recorded. You can go look. But
You're going to give this to us, or?
it's already,
Oh, it is, okay.
it's on, ocarm.github.io/algorithms. And I gave you this sample midterm and then the actual midterm, just for you to have. For chapter 11 can skip 10.7. I'm gonna check that. I think you can probably skip 11.7, but I'll go review it. Please let me.
For chapter 11, you can skip 10.7.
That's wrong.
Yeah. Same with 12.
It's like getting your hopes high and just punching me in the face.
Yeah. Now let's see at the kinds of questions, and I will try to update this as I think of better ways of asking questions, right? Because I'm having a hard time figuring out how to ask questions so that they are not just BS. But high level stuff, right? Like I'm trying to find the right way of asking so that they are specific enough, but at the same time, I'm not requiring you to memorize stuff. That's the. But, so, describe the dynamic programming approach and describe an algorithm that uses it. What's dynamic programming?
Save stuff as you go, so you don't have to recalculate it later.
Break into subproblems first.
Break into subproblems, but the subproblems overlap, right? So you save them so you don't have to recalculate them later.
Memorization.
You can either do it with memoization or actual dynamic programming. Build the table from the bottom up, which is what is regularly known as dynamic programming. And as a good example, number 2, given the following intervals with weights, find the scheduling which will provide maximum weight. Hint, the dynamic programming algorithm uses the equation OPT of j equals max Vj plus OPT of P of j, OPT Pj minus 1. Intervals are open, so a job that starts at exactly the same time as the other one ends is allowed in solution. So what do we do?
So it's comparing what's optimal for the item you're on to what was optimal for the one before it.
Yes, right? So we need to sort them by end, right? P of j is the last one that would still be available, right? And so this is wrongly sorted, right? So we'll start with 1, 3, 11, right? Sorry?
By the end time?
Yeah, we sort them by end time, right? We would start with 1, 3, 11, right? And so we would have So for job 1, I'm gonna number them like this, right? The order if they are here. Job 1, what's its P of J? Actually, yeah, 0. Job 2, so that's which ones could you do beforehand, right? Job 2, I'm not gonna sort them when I number them, right? Job 2, P of J is also 0, right? Job 3, this guy, which ones could I run? 1 and 2, right? So P of J is 2.
Because it ends at 5 and start at 4.
Oh, sorry. Yeah. Oh, God. Then, sorry. I need to renumber them, right?
Yeah.
Because, yeah. So let me copy this stuff here. And so we need to renumber these guys, right? And sort them. Now, for job 3, I could do 1, right? Now, job 4, starts at 7, ends at 8, but I can do up to 2, right? Now for job 5, I can do it starts at 8, so I cannot do the 10, but I could do up to 3, right? Does that make sense? Now my table is gonna be on J, right? Which is the number of the thingy, right? So for the first one, right? It's 0. 1, for getting the first one, I do either use this one or not, right? If I use it, then I'm gonna add the weight to the previous one, right? If not, I would go before, but here there's no before, so I will, right? At 1, right? So that would give me a weight of 11. Now, for the second one, I can either do my weight plus the table of to P of J, right? Which is 0, or use the previous weight. So I actually prefer not to include myself. And so I'm still 11. Does that make sense? Now for job number 3, which is this guy, I can either I can add my weight, sorry, step number 3, right?
Yes.
My weight plus P of 11, that works, right? So I'm going to do 11 plus 7, which is 18.
You plus five.
Oh, it is 5. I'm an idiot. So it's 16. Right? Now for job 4, this guy, I either choose the previous or my weight plus P of 2, which is 11. So I am 7, right?
Yeah.
So I like myself, right? So that's 18. And then for the last one, I can go and do either 18 or 16 plus 5, which is 21. So I like myself. Does that make sense? So this is a standard example of dynamic programming.
Just give us one more second to copy all this down. So
Why are you copying it? Don't.
if I write, it gets into my head
Okay.
better. So.
Okay. I can ask you to do these kinds of algorithms. I will make sure that it doesn't take you an hour to do them if you apply the right algorithm. What is a flow network?
It's got a source and a sink. It's generally directed, and there are weights on the edges. And the source can only have output, the sink can only have input, and every node in between has to have input and output. That you can't have more output than you have input.
Exactly.
You do it, son.
Yeah. And the weight is how much you can send through, right? The algorithm that we use to solve flow problems is the Ford-Fulkerson algorithm, right? And so I could ask you stuff like this. I am not gonna ask you to run a Ford-Fulkerson algorithm.
You're
On
not going
paper.
to ask what? I'm sorry.
To actually run one on paper. I promise. Because there is a limit to how much time you guys have. I tend to plan my tests for. We only have 2 hours, so I'm assuming that for most of you it would take you about an hour, kind of the average. There will be some people who leave at 40 minutes, and there will always be people who will take the full 2 hours regardless of need. That's perfectly okay. People want to check their work over and over. But I'm assuming that about an hour is all we can really ask of your brain. And after that it goes to sleep, whether you are still here or not. That's what happens to mine, at least. So and we had things like how does it apply to other stuff? So how do we apply the maximum flow algorithm to the bipartite matching problem?
Who's Kevin Wayne?
He is a guy at somewhere. Princeton, yes. He is super mannish in this stuff. I think Kleinberg and Tardos are also at Princeton, or at least one of them is. And Kevin Wayne is one of the teachers there, and he's the guy, I'm assuming Sahi, that wrote the data structures book. No. I don't know him.
I think with Kevin, it's a pretty safe bet that's a guy.
I don't know.
My friend named his daughter Wesley, which I wasn't.
Sorry?
My friend named his daughter Wesley, which I didn't know was a girl's name. So
Yeah, there's some that are, yeah.
Gender's a social construct.
It's like the sequel to Boy Named Sue.
Yes, a boy named Sue. Wesley is a guy's name, right? Princess Bride.
Yeah.
No, that was slightly different. Anyway, matching, right? Given a graph, find a max cardinality matching, bipartite matching. Nodes can be partitioned to subsets such that every edge connects a node in L to one in R, and find a max cardinality matching on a bipartite graph, right? So find a subset of edges if each node appears in at most one edge. Find one that has the most, the highest cardinality. We can do it as a max flow by creating a digraph with the left and right, and then create a new SNT. Direct all edges and assign infinite capacity, add source and sink, and add unit capacity that go and unit capacity that come here, right? And that will actually, a max flow, right, will give me that cardinality. And it will be using the appropriate edges over here. So it is, that is one of the most important concepts, I think, of techniques in general of this class, right? It's like, oh, I can change something that looks like this problem into something that looks like this other problem. And that one I know how to solve. So. I could ask you some other things from that chapter that were similar, right? Then we get into fun stuff. P is a proper subset of NP. Is that true, false, or unknown? P is a possible improper subset of NP. True, false, or unknown?
True.
It's true, right? We don't know whether the equal part is there. NP complete is a subset of NP.
True.
Who said false? What's an NP complete problem?
I thought NP complete was a problem that every NP problem could reduce to.
Yes.
Yes.
But it also has to be an NP problem.
Okay. See, I was getting subset of and polynomially reduced to confused.
Yes. In this case, right, it's a subset. So basically, the set of all NP complete problems, right? Every NP complete problem is also an NP problem.
But not NP hard.
NP hard doesn't have the requirement that it's NP,
Okay.
right? But NP complete is a subset of NP hard. Co-NP is a subset of NP.
Can you refresh my memory on co-NP?
When we look at them as decision problems, right? an NP problem has an algorithm for saying yes, but may or may not have one for saying no, may or may not have a polynomial witness for saying no. Requires, for the witness, requires for yes, but not for no. The co-NP is the reverse, has one for no, but may or may not have one for yes. And
I would say false.
it's probably false, but it's unknown, because they may be equivalent. They may be the same set.
So do we get extra credit if we prove that theorem?
Yes, absolutely. You get extra credit and instant fame. How can I do this? Every NP hard problem is also NP complete.
No.
No. False.
False, right? We just said it.
Yeah.
The other way around. Every NP complete is NP hard, but not the other way around, right? NP complete is NP hard and NP. Yes, you need to keep those definitions straight. I could ask it 7 different ways, right? There's 5 combinations, and you need to know the definitions, and then answering these things is not hard. If you try to remember every possible combination, some of you can. Some of you are really, really good at memorizing, but
There's no chance that you'll let us bring in a single page of a cheat sheet that we wrote on our own.
there's, sorry?
There's no chance you'll let us bring in like one sheet of our own little cheat sheet.
No.
No.
That would, no.
How about an index card?
An index.
That requires a different exam. You don't want that.
Fair enough.
Right? I mean,
Yeah. Fair enough. Never hurts to ask.
you don't want. You don't want that. List and describe 3 NP complete problems. 3 side, yeah.
Circuit set.
Circuit side, yeah. All the sides. Side, 3 sides, and circuit side. Other ones. No?
They're satisfied.
Coloring. Don't look.
For the 3 set, you have 3 binary variables and you have ors. I'll stop talking.
Traveling
The end of this guy? Or the end of the other guy? We have circuit set, tree set, independent set, vertex cover, set cover, directed Hamiltonian cycle, TSP. You should definitely know TSP, right? You should definitely know knapsack. Those are famous and they don't have anything special. Integer knapsack. Tree coloring on graphs or planner, and subset sum, scheduling. There is more.
What was the first one you said we should know?
Um,
It sounded like you said knapsack, but
knapsack, yes.
oh, it is knapsack. Okay.
Yes. The integer knapsack problem
Okay.
is NP complete. Backpack problem. I have no clue what's a knapsack. They always translate it as backpack, so I assume that is a backpack. It's something like that, right? It's not necessarily a backpack, it's some kind of sack.
It's basically a backpack.
It's a backpack?
It's basically a backpack.
Oh yeah, I remember each of the
Yeah.
the different items in different weights. You determine your okay.
there is even a bigger list.
I have a list pulled up on Wikipedia.
Ah, okay. That also works. Factoring, primality testing. No. I think that is the last list that they have. There's a bunch of them throughout the slides, right? They keep completing it. For one NP complete problem of your choice, show how we know it is NP complete by reducing it to another known NP complete problem. We spent 2 weeks on this, right? You should know at least a couple. You probably should remember, right? You probably should go read all of them, but you should definitely know at least a couple. I will probably ask you something like that, or give you, out of these 3, right? Describe one or something like that, rather than require you to memorize all of them. Describe the p-space kind of problems. What's p-space?
Except polynomial space and its execution.
Polynomial space, right, rather than polynomial time. So it is slightly bigger because you can't reuse. You can reuse space, you cannot reuse time. So polynomial space is actually slightly, allows you to do slightly more, potentially slightly more than polynomial time. Actually, if again, we don't know whether they are. P-space, proper subset, bless you, of NP. It is unknown because they may be the same. Maybe. Right? They are probably not. But and NP is a proper or improper subset of P-space. That's true, right? Describe one problem that's in P-space but not known to be in NP. Planning is one. Again, there is a whole bunch of them. Not a whole bunch, but a few. Quantified satisfiability planning. QSAT planning. Do we have more examples? There is some other ones, but QSAT and planning are kind of the ones that come to my mind. Then we go into the stuff that we covered at the end. What are the 3 relaxations we can make to solve NP-complete problems in practice? Either time, right? So don't take polynomial time. Optimization, don't make it optimal.
In the cases, like
Or, yeah. Deal with special cases rather than solve every problem.
No, I wasn't gonna get it. I was glad you did.
Describe one of the algorithms that work in special cases for otherwise NP-complete problems. You can go look. There's a bunch of algorithms that work on trees, whereas they don't work in graphs. For all of the graph things, there is also one that I normally like is the knapsack, again, the integer knapsack. We have a dynamic programming that uses the weights as one thing on your table. So you can do it, if for small weights, it works. If the maximum weight is small, then it will work. But if your weights can be huge, then It's horrible. Go read chapter 8. Go read chapter 11. Except 10.7. Sorry, I will fix that typo. Briefly describe the simulated annealing algorithm. What's the metropolis algorithm? Simulated annealing.
Yeah, I don't remember the simulated annealing algorithm.
It is a variation on metropolis, right? The metropolis algorithm is hill climbing or gradient descent with probability. So rather than only go towards the towards one that is better, have some probability, and if it's worse, go there with even with some probability, depending on how much worse it is. Simulated annealing includes a parameter, temperature, that determines that probability. So you start with a high temperature, so you could explore more, you could take more false steps, and you go reducing that temperature over time. So that at the end you're doing almost basically hill climbing. Describe one of the randomized algorithms we studied.
I remember that. My paper's on a randomized algorithm. The pages on it.
And what's the difference between Monte Carlo and Las Vegas algorithms?
Monte Carlo finishes in polynomial time but doesn't guarantee a solution.
And Las Vegas does the other way around, right? So contention resolution was one of them. Min cut, we saw one. There is primality testing also. We didn't really see it. But contraction for min cut. This is not an algorithm. There's one for max tree satisfiability, which is just doing at random, right? That gives you 7/8 of a chance. So if you do it a bunch of times, right? And Monte Carlo runs in polynomial times, is not guaranteed to find an answer. Las Vegas is guaranteed to find the answer, but it's only probabilistically runs in polynomial time. So again, go look at these things, right? Any questions?
So, as for studying the comprehensive nature of the exam, is there going to be any, lots of times when you take a comprehensive final exam in a class like this, they will lean more towards the new
Oh,
stuff.
definitely, absolutely.
Okay.
I would assume, especially this class didn't really build a lot on the previous stuff, right?
Mm-hmm.
For some of the other, like for my programming class, well, of course it's comprehensive because I'm going to ask you if statements, right? I mean, the stuff that I'm going to ask you has if statements, even if that wasn't the first. In order to ask you the more complicated stuff, I have to ask you the simple. This one didn't really, there isn't as much building from previous stuff. So I would say this one is probably, it's not a promise, but I would assume something like 20% from the previous stuff and 80-ish% from this stuff. Which doesn't mean that you shouldn't know all the other stuff, right? I mean, it's just, also this stuff I think is way more than half compared to the other stuff. Right?
And kind of on top of that, when are you going on your trip in terms of like communication with you? Is there going to be a
I will have email.
Okay. So
I'll
you-
always have email.
Okay.
I'll always have my phone actually, too. And it works wherever I am.
Okay.
Yeah, technology is cool. I think all of them do, but I have T-Mobile because it gives me free long distance to Mexico and I can use it in Mexico. I think now everybody else does, but no.
You do, you just gotta.
Just gotta pay?
Charges you for anything outside.
Oh, I thought at least AT&T does, but I don't know.
There's an America's program that you can get apparently.
Ah, but it's not. Yeah. T-Mobile is automagical. It just works, which is amazing. It's like, oh, that is so cool. I used to buy phones with like dual SIMs and stuff, so I could do those horrible things. I don't need to do that anymore. Maybe I'll go to Europe and I'll have to do that anymore, but I won't complain if I'm in Europe.
You can do like, well, you can, at least for AT&T, which is what my company uses, you do like 30-day programs where you just,
Okay, pay 10 more bucks and
yeah, just don't be posting videos on Facebook and all the time.
yeah.
I was buy a local SIM in whatever country.
It's so nice to not have to do that in Mexico, which is where I go. Any other questions that don't have to do with cell phone? No, but I will have my phone. I will have a computer. I will have internet.
Cool.
Your
I
wife
will
do-
be sober at least some of the time.
Your wife doesn't bar you from your devices when you're visiting family.
No, I'm actually not visiting family. I'm going to 2 different conferences.
Oh,
One in. I just went home last weekend. I'm going to 2 different conferences. One of them is in Mexico and one is in Vegas.
Okay.
So
I'm good.
And the final is the 11th at
the
6?
final is the 11th at 6, right? We all agreed?
December
was
the
it?
11th.
Yes.
It's even later than
Or was it?
No, it's not the
December
11th. No. Wait. The 11th is those guys.
Oh.
It is not the 11th.
Yeah,
It's like I could have sworn.
6, yeah.
Submission of the paper. It is whenever it says it is.
Tomorrow.
Yeah.
Actually, like midnight. Can you like push that back one day?
Now I'm gonna. Now that we got to the deadline, I'm gonna move it until the Monday after Thanksgiving.
Oh,
But if I don't do that, then you don't start until Sunday after Thanksgiving, right? So. That's how it works, right?
Also like the 20th.
you got a judge, huh?
MW
20th.
You see the guy now.
5 p.m. Wednesday, December 6th
December 6th.
at 6 p.m.
It's
We'll be on that show.
trick I found it.
We'll
Switch
shut
your
it.
font to Arial.
I know it's bigger, but I can't stand typing.
Right?
Oh no, you write the whole thing in Times New Roman and then switch to Arial at the end.
Cool.
Switch to Arial.
And let me stop the recording.